Okay, good evening, dear students. In last class, we discussed the variation of free energy with temperature and pressure, and another one concept is of Gibbs-Helmholtz equation. You derive separately. One is the Gibbs and one other is the Helmholtz. The combined equation is Gibbs-Helmholtz equation. The combined equation, the two combined equation is called as the Gibbs-Helmholtz equation. Okay. In today's class, I am going to discuss about the Clausius-Clapeyron equation. Main thing is thermodynamics. Thermodynamics. Thermodynamics 2. Here, derivation of the Clausius-Clapeyron equation. Clausius-Clapeyron equation. This is very important for 5 to 6 marks question. There is a 5 marks question. This is 5 marks question. Clausius-Clapeyron equation. Clausius-Clapeyron, C-L-A-Y-P-E-R, Clapeyron, Clausius-Clapeyron equation. Here the Clausius and Clapeyron. Those are the two scientists. One is the Clausius equation and another is the Clapeyron equation. This Clausius equation, here first is Clapeyron equation. The Clapeyron equation is then modified as Clausius, and then equation is called as a Clausius-Clapeyron equation. Okay, here you consider the 1 gram mole of a liquid. You consider the 1 gram mole of a liquid. 1 gram mole of a liquid. Consider 1 gram mole of a liquid that is confined in a cylinder by a frictionless piston. It is confined by a cylinder with a frictionless pressure. Frictionless piston. Frictionless piston. Frictionless piston. And here let the volume of the liquid be V1. Volume is a V1. Volume of the liquid is V1. You take volume of the liquid is a V1, and its vapor pressure equal to T. This is a vapor pressure. Vapor pressure is equals to the P is a vapor pressure, V1 is a volume. And next, now to allow the liquid to evaporate, here consider the 1 gram mole of a liquid, and this liquid is allowed to evaporate. Here liquid is allowed to evaporate reversibly at a constant temperature. Temperature is a constant. Here temperature is constant, and when the whole of it has evaporated, all the liquid is whole is evaporated. Whole liquid is evaporated, and the volume of the vapor will be V2. Volume of vapor will be V2. See here. You taken a 1 gram mole of a liquid, and it is allowed 1 gram of a 1 gram mole of a liquid, and the volume is considered as a V1. then this liquid is allowed to the evaporate. After they evaporate at a constant temperature. This is a vapor pressure. At a constant temperature, it allowed liquid to evaporate and then the final get the volume of vapor will be V2. Here consider the volume is V1, V2, pressure is P and temperature is T. This is a constant temperature. And therefore the work done during evaporation. How much? Here the work is done here during the evaporation. Here liquid is evaporated. Here in liquid is evaporated, some work is done here in a evaporating of liquid. Okay, therefore the work done is right here the equation. Here, therefore, work done. Therefore, work done during evaporation. During work done during evaporation. Work done during evaporation. Work done during evaporation. Work done with W. During evaporation is here the presence of pressure and the volume is V2 to V1. V2 minus V1. Work done W is equals to P, that is the pressure, and here V2 minus V1. This is equation number 1. You write this is the equation number 1. After you differentiate this equation, W is equals to P into V2 minus V1 with respect to temperature, and V2 minus V1 is a constant. Here you differentiate this equation 1 with respect to the at constant temperature, and this is a V2 minus V1 is a constant, and we get differentiate equation 1. Differentiate equation 1 with respect to temperature. With respect to temperature. With respect to temperature at constant V2 minus V1. Okay, V2 minus V1 we get V2 minus V1 we get, that is dW with respect to temperature, dW divided by dt. dW divided by dt means with respect to temperature. This is equals to the dP by dt. V2 minus, this is a constant, V2 minus V1, and remaining dP, differentiation of pressure divided by differentiation of temperature. And this is equation number 2. This is equation number 2. And here the heat is absorbed. Heat is absorbed from the surroundings. Here the heat is absorbed from the surroundings is a latent heat of vaporization. Heat is absorbed from the surroundings. Here heat is absorbed from the surroundings. From the surroundings. Heat is absorbed from the surroundings. It is absorbed from the surroundings is the latent heat of vaporization. Is the latent heat of vaporization. Latent heat of vaporization here. You consider as a here. latent heat of vaporization L, and which on substitution in the first law of equation here, first law of thermodynamics. Here the latent L is substituted in the first law. First law is of delta E is equals to Q minus W. In Q, you add latent heat, that is of L. Therefore, delta E is equals to L minus W. Delta E is equals to L minus W. This is equation number. Okay. Here delta E is equals to L minus W. This is equation number 3. And here on substitution of x, first the equation number 2 and 3. Here the substitution of expressions, that is this equation number 2 and this one equation number 3 in the Gibbs-Helmholtz equation. You substitute equation number 2 and equation number 3 in the Gibbs-Helmholtz equation. Substitute equation 2 and 3 in the Gibbs-Helmholtz equation. In the Gibbs-Helmholtz equation, we get Gibbs-Helmholtz equation. We get, that is W plus delta E. Here the Gibbs-Helmholtz equation, W plus delta E is equals to T into dW divided by dt. dW divided by dt. But this is a Gibbs-Helmholtz equation. You substitute here the equation number 2 and 3 in a Gibbs-Helmholtz equation, that is W plus delta E is equals to T into dW divided by dt. Okay, here W means here this is a dW, W plus delta. Okay, this is a W plus delta E means delta E means L minus W. L minus W is equals to, W is same here, W plus delta E means L minus W. L minus W is equals to T. Okay. Here dW divided by dt. The dW divided by dt, this is you substitute here dW divided by dt. This equation is the dW divided by dt. Here V2 minus V1, T into V2 minus V1 dt divided by dt. T V2 minus V1 dt divided by dt. And finally you get L is equals to T dt divided by dt into V2 minus, here this is a W plus L minus W, plus into minus minus, plus into plus, plus L, plus into minus minus, W plus L minus W, therefore is equals to T into dP divided by dt into V2 minus V1. Here plus W minus W. Here L is equals to T into dt divided by dt into V2 minus V1. You substituted these two equations in the Gibbs-Helmholtz equation and you get a L is equals to T dP divided by dt into V2 minus V1. We can write here, that is the dP divided by dt, dP divided by dt is equals to L divided by t into V2 minus V1. L divided by t into V2 minus V1. L divided by V2 minus V1. Okay. This is a one equation. See here. You write or t dp divided by dt V2 minus V1 is equals to L. Here. The remaining here dp divided by dt, that is equals to this one L. The multiplication comes in a division t into V2 minus V1. See, dp divided by dt is equals to L divided by t into V2 minus V1. This is a dp divided by t is equals to L divided by t into V2 minus V1. This equation is known as a Clapeyron equation. This is the Clapeyron equation, and this is in a general form. It is written as dp divided by dt is equals to delta H divided by V2 minus V1. This is Clapeyron equation. Clapeyron equation. This is the Clapeyron equation, which in its general form may be written as general form may be written as dp divided by dt is equals to delta H latent heat. L is a latent heat. It is a heat. Delta H divided by enthalpy change in enthalpy. Delta H divided by T into V2 minus V1. Can write this equation here. The general form of this Clapeyron equation is dp divided by dt is equals to the delta H divided by T into V2 minus V1. Here dp divided by dt is equals to delta H divided by T into V2 minus V1. Where delta H is the heat of transition, where delta H is the heat of transition, and V1 is a volume, and V1 is a volume of definite weight. And 1 gram of changes to volume due to same weight. Here 1 gram changes of volume in same weight. V2 is a 1 gram changes of volume in a same weight. And T is a temperature. This is a T is a temperature. And then dP is a differential pressure, dT is a pressure change here, temperature. Then delta H is a heat of transition, V1 is a volume of definite. Here the volume of a definite weight, and here V2 is a 1 gram changes. Here only 1 gram changes of a volume in a same weight here. In that same weight, here the volume is changes. Here consider as a liquid is V1 is a liquid, and evaporating afterwards you get a V2 gram. In that same weight, you get a same weight, and you get a V2 is a volume, vapor of volume. Here this is a V2. This temperature T is a temperature. Okay, then you get dP divided by dt is equals to delta H divided by T into V2 minus V1, and this is equation number 3, and here the equation number 4. This is the equation number 4. Next, the equation number is then modified. It can be simplified. That the above equation, that is equation number 4, can be simplified by neglecting the small, that is a volume here. The neglecting the small volume of the liquid. Here you are like neglecting small volume of the liquid in comparison with the volume of the vapor. Here the small volume of the liquid in comparison with the volume of vapor from equation 1. Then this equation in such case becomes, that is only dP by dt is equals to delta H divided by T. And here you are neglecting here. Therefore, modified above equation 4, neglecting small volume of liquid comparing volume of vapor. Then the equation 4 becomes dP divided by dt is equals to the delta H divided by T into here this general equation of Clapeyron equation. This general equation is modified, then neglecting the small volume of liquid and comparing volume of vapor. Then this equation number 4 becomes, that is dP divided by dt is equals to delta H divided by T. V2 minus V1 is comparing, it is neglected. Then you are taking the V here, small value, and the equation here, this is the equation number 4 and this is the equation number 5. Here dP divided by dt is equals to delta H divided by T, that is equation number 4. You know that here PV is equals to RT. We know that PV is equals to RT. We know that PV is equals to RT. Here you take V is equals to RT divided by, you substitute V value in this above equation. Here you get PV is equals to RT is a gas constant. Here this is the equation, gas constant equation. And then the volume you take here, this is a V, volume V is equals to RT. This is goes to in a division, in a denominator. V is equals to RT divided by T. And this volume, this V value, substitute in the equation number 5. Substitute V value in equation number 5. In equation 5, we get here we get that is dt divided by dt is equals to delta h divided by t. Here see delta h divided by p. Delta h divided by p means multiplied by p. Multiplied by p means here rt. B is this one rt divided by. Okay. When it is multiplication, it goes to multiplication. You get a p divided by rt. Here therefore dp divided by dt is equals to the delta h divided by t rt in p delta h p divided by p rt and p rt t into t square. You get a t square. Final equation dp divided by dt is equals to delta h p divided by rt square. Okay, right here. This is a continuation. This continuation continue. Continued equation. I will start from here. See here equation is dp divided by dt is equals to the dp divided by dt is equals to delta h divided by here. This is goes to the numerator. Here delta h multiplied by p divided by here. This t rt t into t square r t square. We get the r t square. That is r t square. dp by dt is equals to delta h p divided by r t square. Or write over r 1 by p. Here we are taking 1 by p multiplied by, we are taking this side 1 by p dp divided by dt is equals to remaining delta h divided by r t square. Okay, this p is, you are taking this side 1 by t multiplied by dp divided by dt is equals to delta h divided by r t square. This is, you consider equation E. Okay, next we know that 1 by p multiplied by dp by dt is equals to delta h by r t square is a d log. 1 by p, we know that 1 by p multiplied by dp divided by dt is equals to the d log base T pressure P here. D log T pressure P divided by dt. You take, this is a equation number 2. Okay, here 1 by p multiplied by dp by dt is equals to delta h divided by rt square. This is the equation number A. Here the completion of equation number 5. In that equation number 5, and this is then rearranged here. Then rearrange equation, you get dp by dt equals to delta h p divided by rt square. And next it is then rearranged 1 divided by p multiplied by dp by dt is equals to the delta H by RT square. That equation is considered as a A. And next, then 1 by P, we know that 1 by P into dP by dt, this is equals to d log EP divided by dt. Okay. Next, finally, we get, you substitute this value in this equation. That is d log PE. This equation, you substitute this value in this equation number E. Then we get d log base E, P pressure divided by dt is, we get delta H divided by R T square. This is equation number 6. This is equation number 6. Okay, here d log E P divided by dt is equals to the delta H divided by R T square. And this equation is known as the Clausius-Clapeyron equation. Equation number 6. Equation 6 is known as equation number 6 is known as Clausius-Clapeyron equation. Clausius-Clapeyron equation. Okay, up to here. This you derive in examination. This is a derivation of the Clausius-Clapeyron equation. Next, the application of Clausius equation or a Clausius-Clapeyron equation. Okay, next, applications of Clausius-Clapeyron equation. Applications of Clausius-Clapeyron equation. Here there are 3 applications. One is a calculation of latent heat. Here, the first one is a calculation of latent heat of vaporization by knowing the values of vapor pressure of a liquid at 2 temperature. Here, first one is a calculation of the latent heat of vaporization. The latent vaporization. Calculation of latent heat of vaporization. Latent heat of vaporization. This is the first one. Here, for finding or calculating the latent heat of vaporization, you know the value of the vapor pressure of a liquid at 2 temperature. 2 temperature means that is the T1 and T2. You know these 2 temperatures. T1 and T2. The and pressure is a P1 and P2. You know these 2 values. T1 and T2 and T1 and T2. That is this is a temperature and this is a vapor pressure. And the molar heat of vaporization and latent heat can be calculated. Here, molar heat of vaporization and latent as well as the latent heat can be calculated. We know these two values. This is a first application. Next, second is a calculation of boiling point or a freezing point. Calculation of boiling point and freezing point. Freezing point. Here the calculation of boiling point or of freezing point. Here by knowing the calculation takes place by knowing the value of freezing point. Here you know the value of freezing point or the boiling point. You know this value or this value. You know freezing point value or the boiling point value of a liquid at one pressure. It is possible, you know, at one pressure, that is P1 pressure and P2 pressure. You know any one of the pressure, you know the boiling point or a freezing point at one pressure, and it is possible to calculate it another pressure. Possible to calculate the another pressure by the use of Clausius equation. This is a second application of Clausius-Clapeyron equation, that is calculation of boiling point or freezing point. Third application, calculation of vapor pressure at another temperature. Calculation of vapor pressure at another temperature. Calculation of vapor pressure at another temperature. Here, if the mean heat of vaporization, the calculation of vapor pressure at the other temperature. Here, the heat of vaporization is available. Here, the heat of vaporization is available, and it is possible to calculate the vapor pressure of a liquid. Here, it is possible to calculate the vapor pressure of a liquid. Already available the heat of vaporization. You know the available heat of vaporization, and it is possible to calculate the vapor pressure of a liquid at a given temperature. Here, vapor of a given temperature. If the vapor pressure at another temperature is known, one temperature is known and vapor pressure one value is here, the latent heat of vaporization value is known and one temperature value is known, and then easily to calculate the vapor pressure of the another temperature. These are the applications of Clausius-Clapeyron equation. Here Clausius-Clapeyron equation, there are three applications. Here first one is a calculation of latent heat of vaporization. Second one is a calculation of boiling point and freezing point. Third one is a calculation of vapor pressure at another temperature. Okay, I'll stop here only. I'll continue next class. In next class, I'll discuss the criteria of spontaneity or irreversibility. Here comes some conditions of criteria of spontaneity, that is a irreversible reaction. And here some conditions are occurred in equilibrium state. Okay, these are the conditions of equilibrium are discussed in next class. Thank you.